Let's go through Equal 239 sliding window maximum. For this question, it gives us an integer real numbers and integer k. And it has a fixed size sliding window with size k, slide from left to right. And for example, k equals 3. And so the first window is 1, 3, minus 1. And it has a maximal value to be 3. Then 3 minus 1 minus 1, it has a maximal value to be 3. And when sliding this one has 5, and this one has 5. And it goes to this window, it is 6. And this window it is 7. So to return for every window, the maximal size, max value. So we know if we do brute force for each window, it will be O n k time complexity. And if we thinking about using a sliding window and a heap, that will be O n log k time complexity. And we can do better. That we can think about if there is a data structure, for example, we push in those kind of data and into our data structure. And the thing is that if on the right side there is an element is greater than left side, and that means, for example, this is num I and num j. If they are still in the same window, that means the maximum will be num j, and also because if num j is in a window, because num I will be slide out of window early, so that means num j will always be optimal than num j. Num j will always be optimal than num I if there is a number that is higher and the index greater. In this case, that means there is no meaningless. That it will be meaningless if we still keep these values, right? So if in this case, we can have the later data trying to pop out the previous data, right? If they are still kept in the K window, right? K size window, because it will never be in any window on the left and smaller number to be a maximal value, right? So we in this kind of situation, we can get rid of I. And there is some other situations on the right hand, the K, right? Not K, L, nums L. The index is on its right, but the value is smaller, right? We still need to keep this kind of value because it is possible nums J being moved out of the window earlier, right? So nums K is still possible to be num L still be possible to be some kind of sliding window max, right? So in our data structure is that we are going to keep those kind of value on the right, and it will be in a decrease order. If there is some kind of on its right, if there is some kind of greater one, right, we can safely pop out those kind of value, right? Because if they are in the same window. So we need a data structure can move data from this side, right? And also, when if for example, if we go to this kind of index, for example, X, right? Some of the data which is smaller than um, uh, moving outside of this kind of window, right? Um, then we should move those kind of data from the left side. So we need a data structure which we can move those kind of data from right, and also when it's outside of the index move from the left, right? So for moving out of the left, that is out of the I minus k window, right? Um, so this index will be I minus k plus one, right? If it is still not being popped by this kind of set. So we use some kind of data structure which can pop left and pop right. To the maintain of the left side is maintain the index to keep the size k window, and pull from the right is just moving those kind of useless data. For example, we have a number which higher value, and also on its right, that means the same window which have lower value, and to its left, but never being the maximum. We can remove that. So in the case, in the final, what left on this kind of data structure is like decreasing order values, right? So we use and also this kind of because they are decreasing, right? And also we need their structure need to be pulled from the right and pulled from the left, right? So we use a Q. This is a pull first. It's pull first method, and this is pull last method. So because the data are maintaining a decreasing order, so we use something called a monotonic queue. So let's write code for this. Um, and doing like this, every item will be enqueued now and dequeued once. So the time complexity will be O(n). And there are at most the k items in the data structure, so the space complexity will be OK. Let's write code for this. The n equals nums, the length, and we're going to have result equals new int n minus k plus one, right? So we need a data structure which you can pull from left and pull from the right. So what we write is for int I put there I smaller than n I plus plus. So let's say if this kind of deck is not empty, and on its left side, this kind of index is out of K window, and I manage that pick first. If this is uh, greater equal to K, right? Then we can that means this kind of index the on this deck on its left, right? Those kind of index, it will be we're going to pull out, right? So we are going to because they are not in the case size window, so we are going to have deck for left, for first, not for left, for first, and also we'll say those kind of maintained in this deck, they are in kind of decreasing order, right? And now if we come in data which on its right, it's so this kind of size, right? It will pull any on its left any value which is smaller than this nums r, right? So we'll pull out this until, and then we put this one. We are keeping this and this, right? because this will never been the candidate of the next slide window, which have the highest value anymore, right? Once this enter our window. So we write a while loop here. While um, Q is not empty, right? That is not empty. And nonce that pick pick last, right? If this one is smaller equal to, uh, if it is equal, we can also be able to safely remove it because the index is on its left, right? So we're going to have a deck for last. And for any monotonic queue or monotonic stack, right? The things that we after those kind of while loop, we should still um you add value, right? So in deck we have something called add last, right? So deck add last, and we always add I, right? So here, if we write if I is greater equal to k minus 1, right? Then what state um, on its left, this kind of data structure is the window max. We just use a pick first to get this value out. So we are going to have result I minus k plus 1 equals deck pick this is the index, right? So we still need a nonce pick first. And in the end, return result. In the Python code will be similar. We need a use deck, so we need a import the deck data from collections, right? Collections import deck. And we are going to have let's have a inter and result EQ. N is the length of nonce, and the result um, being array, right? That is the size is actually n minus k minus plus 1, right? And this will be deck. So what we write is for I in range n, right? And first, let's check the deck, the left index, whether it is out of the range, whether because it may need to be I minus k plus 1, right? So if it is smaller equal to I minus k, then we need to pull left. So let's say if deck is not empty and dq0 is smaller equal to I minus k, right? In Python, it is called pop left. EQ the pop left. And um, here, this step we just use if because this I is moving just index by index, right? So we don't need a while loop. Just use if um, it is fine, right? But for sometimes, if it's not the index is not consecutive, we may need to use while. But for this question, if it's enough, and we'll write uh, while stack is not empty, and the nums stack, the last one, right? So we can -1 is smaller equal to nums I. That means the index I will be more useful than any previous numbers, which satisfies this kind of condition, because the previous one index is left and the number value is smaller. It will once I is in this K window, right? This will never be any maximal or any forward upward K set window. So we can have this one pop, right? So this is pop actually is in Java is pull last, right? Pop left is pull first. In Python, it is pop left and pop. And after this, we'll always have dequeue append I. So I write if I is greater equal to k -1, we're going to have result append nums dequeue 0, right? So this is a pick pick first in Java, it is pick first. In the end, we just return result.